Hey, hello everyone. We will get started. First thing I want to note, most important thing, before I see you guys next Wednesday, you will have a test. Okay, so just make sure that you complete the test. I'm going to share my screen. Just for being overly redundant, we'll go over where it is. So when we open up Moodle, you will see that there is a section, you can find it on the side here, which is chapter tests and final exam, or you can scroll down and get it there. You'll want to take test 1. So it will open on Sunday at 5 a.m. You don't have to take it at 5 a.m. I just opened it then. Sometimes people like to take things at weird times, but I wanted to give you a weekend day and a weekday, depending on how you work. If you work on the weekends or you work during the weekdays. So you'll have Sunday 5 a.m. through Monday at midnight. So if you're, kind of busy, you can just plan during your lab time to take it. Once you click on it and you activate it and you start the exam, you only have the hour and 30 minutes to complete it. So it's not like a pick and choose. I'm going to answer 5 questions and then come back to it later. You need to sit down and take it. I'd recommend having this periodic table and formula sheet out. So if I click on this here, there's a periodic chart and a formula sheet. It's also in the back. Both of these things are in the back of your lab manual on the last 2 pages. They just have like quick reference stuff. So you may want to have that available for the test. That's what I would traditionally give on an in-person exam. So I tend to kind of like work the tests with those conversions and things. Not only will you have the test though, you'll also have homework, and you'll also have mastering chemistry quizzes and the labs. So just make sure you're turning all those things in. As far as lab turn-ins, I've had about 13 turn-ins for each lab thus far. So that's a little shy. I think there's a couple people that are missing them. Hopefully it's just you're missing just the first one or so. Please, everybody get on turning those in. All right, let's go to the slides. So we finished up, we've been talking about the periodic chart. And we stopped here with this guy, Dmitry Mendeleev. So he was a Russian chemistry professor, a really, really smart guy. They say like there's a fairy tale sort of idea that he was like on a train going Trans-Siberia, and that he had the first 20 or so elements, each one on a card in a deck of cards. And he was like rotating through the deck of cards, trying to see how the elements related to each other, because he didn't have a periodic table. He made the periodic chart, right? He made it. So, but he didn't have any instruction on like, how should I organize this? Should I organize it off of properties? Should I organize it off of, the number of protons? What should I do? And so he decided to put them in order of increasing mass. He had the lightest one first and then went to the heaviest one. And what he found when he kind of laid these cards out is that hydrogen had its own unique properties. It did its own thing. Helium had this property, we'll just call it green, okay? Lithium had this property pink, and beryllium had this property orange. And then there was like a varying amount of properties. And then we had fluorine. And then what he found was that neon had this similar quote unquote green property. Let's say the green property is a property where the material doesn't like to bond with other things. And he saw that neon was very similar in property to helium. And then it went to that sort of pink property, and then it went to that orange property again. And he saw that there was this repeating pattern over and over again. And so he thought, well, in order for convenience, why don't we truncate the list of elements when we get that repeating pattern and just insert it underneath? So right after neon, he cut everything off and took the sodium and stuck it underneath lithium, right? And he took the helium and put it over neon. So now we're starting to see the basic structure of the periodic chart. And it's ordered not just by increasing atomic number and increasing mass, but it's also got this ordering where things within the same column have similar properties. Okay, so lithium is much more like calcium, or rather potassium. So these two guys, even though they're 2 steps away from each other, these two are much more similar than lithium is to beryllium. All right, neighbors aren't alike side to side, but neighbors up and down in the same building, they are pretty similar, and that they react in similar ways. So this is awesome. I mean, this is so cool that this is the start of the periodic chart. He had absolutely no idea why this was the case. He didn't know why the things in this first column behaved similarly, why the things in the final column behaved similarly. He just, out of observation, organized it in that way. We will talk later on about why these things behave in similar ways in each of the columns. For now, you're just going to trust me and say, yes, everything in column 1 behaves similar. So that's one way that we can organize it, is thinking of columns. Okay. Another way is to distribute out metals and non-metals. So on your periodic chart, if you have your lab manual, you can pull your periodic chart out on the back. It can be good to like take notes on it and stuff. So there's this zigzag line, and it starts underneath hydrogen, and then it comes down around boron and silicon, and it zigzags all the way down. This is the general line, that separates metals from non-metals. Everything to the left and down of the zigzag line is classified as a metal, and that includes the lanthanides. So we can see down here, there's this group of elements. These are known as the lanthanides. They insert, and the actinides, these insert right in here. So if you go to like our row 6 here, it's not like we go from element with 57 protons to an element with 72 protons, and we just don't have any of the other proton or atomic numbered elements. We do. We have 58 through 71. It's just that they've been inserted down here. Okay, so we would sort of take this and like appendix it in there, and you'd have an additional stair step down at this point here. Why don't we put these in here? It's just more convenient to put it on a sheet of paper if we pull those out. All right. So as far as the metals are concerned, it's really everything down and to the left of our zigzag line that includes these. And that's like a majority of what we're working with. So a lot of the things that we encounter in elemental form are classified as metals. Non-metals are going to be things that are to the upper right of the zigzag line. And then we have these things that kind of hug the zigzag line that are known as metalloids. I don't stress so much about metalloids. I really want you to just be able to identify metal from non-metal, right? And like so much of our class is based off of this very, very simple concept, like the way we make compounds and how we name things and how things bond together are really strongly dependent on if things are metals or non-metals. So if I said, hey, cobalt, what is that? You'd be able to say that's a metal. Hey, oxygen, that's a non-metal. Hey, sodium, that's a metal. Because you can find the zigzag line on a periodic chart and identify it from there. So what are some of the properties of metals, non-metals, and metalloids? Well, metals occupy the left side of the periodic table, or lower left. They tend to be good conductors of heat and electricity, so electrons like to kind of move through them. They can be pounded into flat sheets. I don't care quite so much about that, or drawn into wires. They're shiny. This is the important thing, though, down here. Metals tend to lose electrons when they undergo chemical change. If we lose electrons, what's the charge on an electron? Remember, an electron has a negative charge. Okay? So if I lose an electron, what happens to my overall charge? You kind of have to think of these electrons as like negative people in your life, okay? Bad people. What happens when you get rid of negative people? You become more positive, right? So the overall atom, when it loses electrons, becomes positively charged, or it becomes what's called a cation ion. All right, we have 2 different types of ions. The word ion is just a charged particle. Charged particle. It can be a single atom or multiple atoms. If this charged particle is positive, we call it a cation. Some people say, oh, cats are awesome, so that's why it's positive. I'm more of a dog person, so I just look at the T and see that it's positive. No, I just know that a cation is positive, but little ways to remember it. So cation is going to be a positively charged thing. All metals undergo this, okay? All metals like to give up electrons. They don't want to take them on. And that does have to do in a lot of ways with where they lie on the periodic chart. And we'll talk more about that when we get into electrons in a couple chapters. Good examples of metals: iron, magnesium, chromium, sodium, any of those guys on the lower left side of the periodic chart. So non-metals occupy the right side. Oh, and the other thing about metals too is they tend to be at room temperature, they tend to be solid. There is a metal that is liquid at room temperature, that's mercury. But in general, they tend to have like pretty consistent, similar properties. They're solid, they conduct electricity, they tend to be kind of shiny, metallic, and luster. Non-metals, which occupy the upper right side of the periodic chart, have much more varying properties. So you'll find at room temperature, some of them are solid and some of them are gases. In general, as a whole, non-metals tend to be poor conductors of heat and electricity because they don't conduct heat and they don't conduct electricity. They tend to be good insulators. Important thing here that we're going to use a whole bunch is this idea that non-metals tend to gain electrons when they undergo chemical change. So if something is giving up the electron, all these metals are giving up electrons, something else has to be taking them on. Otherwise, we just have this like plethora of electrons floating around. If you gain an electron, remember, think about an electron as a negative force or a negative person. You're bringing negative people into your life. What is going to happen to your overall charge? You're going to become negative. All right. So non-metals like to form what's called an anion. All right. And an anion is just a negatively charged particle. Good examples: oxygen, nitrogen, chlorine, iodine. There are not as many non-metals as there are metals, a lot more metals. So we've got our cations for our metals, our anions for our non-metals. That word cation and anion are used so synonymously with metal and non-metal. Sometimes they'll say, hey, the cation is combining with chlorine. And when they say cation, they mean like a generic metal because that word cation is so strongly associated with metal. We do have these things called metalloids. Okay, those are along the zigzag line. Again, I'm not going to like have you make you identify those or anything like that. But metalloids are important because sometimes they're called semi-metals or they're called semiconductors because they sort of sit between a metal and a non-metal. It's we have this ability to control or conduct their electrical charge. So it's super useful in electronics, easy to flip switches on and off using things like that. Silicon Valley is called Silicon Valley. It's not called, Copper Valley. We don't use large quantities of copper in our electronics. We tend to use things like silicon for our semiconductors. So we've got our periodic chart with metals, non-metals, and then, there's some like metalloids along the zigzag. Another way we can separate our periodic chart is into what are called main group elements and then transition elements. So the 2 columns that stick up on the left and the 6 columns that are up on the right, those are known as main group elements. We call them main group elements because they generally have relatively predictable charges and properties. They behave in a similar way. So everything in this first column here behaves outside of hydrogen. Hydrogen kind of does its own thing. But like lithium, sodium, potassium, rubidium, cesium, they all do a very similar thing. Everything in column 2, again, they behave similarly, so on and so on. These guys in the middle, where it's blue, and this also includes the lanthanides and the actinides, those are known as transition elements. And in transition elements, the properties tend to be a lot less predictable based off of where the element is positioned. So, titanium and zircon, just because they're positioned in this column doesn't mean it tells us anything about their particular properties. Whereas I know that oxygen and sulfur in this column are always going to do a very specific thing when they chemically bond. I have more variance here. Like, for instance, iron, sometimes he likes to give up 2 electrons. Sometimes he likes to give up 3 electrons. It really is kind of unique and dependent on the situation. Okay? The other groups, the main groups, are specific and consistent, and I'll tell you guys about those in a minute. When you hear me say column 1, I'm talking about this, okay, or group 1. When you hear me say group 3, I'm not talking about this here. I'm talking about this. All right. When I call off columns by their number, this is 1, this is 2, this is 3, 4, 5, 6, 7, and 8. I don't really number those because their column placement doesn't say anything about their properties. So if I was to say, hey, what's an element in column 6 that starts with an S? You know, you could come over here, go to column 6 and say, oh, sulfur or selenium. There's 2. So what are the groups? Well, I do think your formula sheet has the names of them, but everything in column 1, kind of minus the hydrogen, is known as the alkali metals. Everything in this column 2, those are known as the alkaline earth metals. Okay, and everything in the alkali metals is going to have similar properties. So again, lithium up top here is much more like cesium than it would ever be like beryllium. We've got our alkaline metals. We have over to the right, we have our halogens. These do have column names, but you don't need to know them. So our halogens are column 7. And then column 8 are the noble gases. All these are gases. The reason that they say that they're noble is because they tend to stay with their own kind. So they don't like to bond very much. And we'll talk later about why these guys in particular don't like to bond. So there's our alkali metals, some properties of alkali metals. They are extremely reactive, really easy for them to react. And they like to react in a consistent way, and that they give up 1 electron. So if I give up 1 electron, I give up 1 negative person, I become positive by a factor of 1, right? So above this column, I want you to put a 1+. These tend to form a 1+ charge. Okay. Why? It has to do with the electrons and their shells and how full they are. We will get into that in chapter 9. So for now, you're just going to trust me and put a +1 above it. Alkaline earth metals. So these guys in column 2, they're also reactive. They're metals. They're not quite as reactive as the alkali metals, but they're still pretty reactive. They differ in that they like to give up 2 electrons. So if I'm giving up 2 negative people, I become twice as positive. So I'm going to put a 2+ charge above that column. This includes beryllium, magnesium, calcium, strontium, and barium. Let's hop over to the other side where the halogens are. This is column 7. So fluorine, chlorine, bromine, iodine, actinide. These are astenine. These have much more varying charges. So like chlorine is like a yellow gas. Iodine is a like dull sort of gray color, and it's solid. If something is giving up electrons, something else is counteracting that by eating the electrons. So halogens, one thing that is very common about halogens is they like to consistently take on just 1 electron. So if I take on 1 electron, my charge will be 1-. Okay, so above the halogen column, or column 7, you're going to put a 1-. And then we've got what else? We have our noble gases. So noble gases, all gases don't really like to bond because their outermost electron shell is full. There's not a lot of incentive for them to combine with anything else. So above this column, you can put like a 0 or a 0 with a slash through it, just to indicate that they're not going to form a positive or a minus charge or anything. Let's fill in some of the other ones. So I'm going to go to this chart here. Okay, so we've got our +1 here, our +2 here. Above column 3, put a +3, but it doesn't include boron because boron's on the other side of the zigzag line. Okay, so the +3 will account for the aluminum, the gallium, and the iron. You can skip over column 4. These guys kind of can do either. They can either take on 4 electrons or give up 4 electrons. We don't really worry about that. This column here, nitrogen, and also phosphorus. Phosphorus tends to do this as well. They will form a 3- charge, meaning they eat 3 electrons. They pick up 3 negative things. Okay. Above column 6, put a 2 minus. And then we already have above column 7, the 1 minus. Okay, so these things like to form positively charged. These things like to form negatively charged. I want you to add a couple other things in. So right in this spot here, like a zigzag line down from aluminum. This is what my brain is flaking on me, zinc. Put a 2 plus. Okay. They aren't in the main group elements, but they behave in a predictable way. So zinc likes to form a 2 plus, and then Ag, which is silver, likes to form a 1 plus. 3, 2, 1. So you will treat these like you treat these things over here. Okay, we're going to kind of have them behave like main group elements. So do you see how they're representing the charge in the upper right-hand corner here as a little superscript? That will always be the placement of the charge. So if you're dealing with a charged particle, that's where it's going to live. All right, so let's go to a whiteboard and play around with some of these. You want to go back here. Yeah, let's talk about this real quick and then we'll go back. So we've already talked about these things called ions, which are charged particles. We have cations, which are positive, anions, which are negative. The charge of an ion is always going to be shown in the upper right-hand corner of the symbol. So you write the symbol of the element, and then if it is charged, they're not always charged, but if it is the charged version, it'll be in the upper right-hand corner like this or like this. And the proper format is to write the magnitude first and then the charge after it. So you'd write 2 plus, 2 minus. If you were to write -2 on a lab or something like that, that doesn't bother me, but no mastering chemistry can be kind of a pain about this. So if it's not accepting it and you're like, I know this is the right answer, it might be because you haven't put the number first. Right? If we're dealing with something like potassium, potassium likes to form a 1 plus charge. I can just put potassium with a plus. Okay, it's an inferred one. I don't have to put potassium 1 plus. I would just put potassium plus. Same thing with something like fluorine. Fluorine is a 1 minus charge. I could just do fluorine with a minus. I don't need to put 1 minus. The 1 can be inferred on the charge, but the 2s or the 3s, you do have to include. So if we look at something that's going to form a cation like lithium, lithium tends to give up 1 electron. Here's the electron that's going away. Bye-bye. What it's left with is what was originally lithium minus 1 of those negatively charged particles, which allows it to be positive. An equation to solve that is this right here. Ion charge equals the number of protons minus the number of electrons. Now, the number of protons never changes, right? If this thing is lithium, it will always have 3 protons. That is what makes lithium lithium. The electrons can change. Traditionally, if we're a neutral element like this, lithium, and it doesn't have a charge, the number of protons and the number of electrons will equal each other. So 3 minus 3 will equal 0, right? But if we're dealing with the charged version, well, I know the charge is a +1. I know proton, there's no debating this. It has to be 3 protons. So the number of electrons will shift. Okay, so we went from 3 protons here in the neutral to 2 protons here in the charged, right? Dropped an electron. That's just a simple equation. It's always protons minus electrons. Don't do electrons minus protons. It'll flip your charge. Also, if we want to get to a charged particle like this with lithium, we never change the number of protons. Okay, I wouldn't keep 3 electrons and drop this to 2, because then we are no longer lithium. What are we? We are now helium. Okay, we've become a new material. So proton number doesn't change. Let's look if we were to add an electron. So if we've got fluorine, fluorine likes to gobble up an electron and form a negatively charged particle. To come up with the number of electrons, you can conceptually think, well, fluorine traditionally has 9 protons and 9 electrons, right? Those numbers equal each other, proton, electron, unless it's charged. If it's charged, we shift the electron number. Well, if it's a negative charge, I have 1 extra electron. Or you can go through and use the equation and say protons minus electrons. So get the atomic number off the periodic chart. If it's fluorine, it's number 9. It's going to have 9 protons. I want the charge to equal a -1. So the number of electrons has to be 10. I have to have one greater electron to give me the overall negative charge. So you are going to want to be able to do that. You're going to want to be able to calculate how many electrons there are and things like that. And let's actually just do that. Okay. So I'm going to write a couple things, and I want you to tell me the number of protons and the number of electrons that they have. Okay, so aluminum 3+, fluorine, with a minus, and sorry, I don't have my periodic chart. What do I want to do? Do calcium 2+. Okay, so for each one of these, I want you to tell me the number of protons, the number of electrons. We'll leave neutrons alone for right now. We'll come back to those. Number of protons is not up for debate. It is unique to the element. So that one should be easy to find. The number of electrons, you'll have to do just a little work for. I'll give you all 2-3 minutes for that. All right. So if you're trying to work on this without a periodic chart, good luck. Okay. You want to have a periodic chart. There's the one you're totally fine using the one in the back of the lab manual. If you have a different one, you can. I have this, I'm borrowing this from my 5-year-old daughter. It's her food placemat, and it is a periodic chart because I'm starting her young so that she can learn all the elements. This one's pretty good though. So there is no debating. Aluminum is number 13, so it better have 13 protons. So actually for both of these, I can write 13. I wanted to start you off with this one so you could see, am I dealing with the neutral atom or am I dealing with a charged particle? If it's the neutral atom, there's no charge here, it's real easy. These two things equal each other, right? In order to get charge neutral, your positive equals your negative. If we have a difference in or we have a charge, then we're going to have a difference in the number of electrons. So my charge is going to always equal protons minus electrons. So charge is a 3+. That is going to equal the number of protons, which is 13, minus some value x, right? The value x here being 10. Or you can think, hey, he's got a 3+ charge. He's gotten rid of 3 negative things. So strip 3 off. Fluorine, is this talking about the charged particle? It's not. There's no charge in the upper right-hand corner. So we're just going to go with fluorine having 9 protons. And in this case, it also has 9 electrons. Bromine, this is looking at the bromine ion. So bromine is number 35. That never changes. If it's bromine, it has to have 35 protons. The number of electrons shifts here though. With a negative, we are adding an electron. We're adding 1 additional electron for 36, right? Or we know that -1 or 1- is equal to 35 protons minus some value x. Well, that value of x needs to be 1 greater than the 35 to give us the 36. Calcium 2+, this is talking about the ion as well. How many protons do we have? 20. How many electrons do we have? Well, a 2+ means I've gotten rid of 2 electrons. So the electron value should be 2 less than whatever my proton value is, or 18. 20 minus the 18 gives me the 2+. This, for whatever reason, this will sometimes throw people off because they think, oh, if I'm getting rid of something, shouldn't my value be negative, right? If I'm getting rid of it, I should become negative, but you're getting rid of something with a negative value. So you become more positive. You've got to think of what are you gaining and losing? You're losing something with a negative charge. Any questions on this? You want to be able to do that. Remember the positive guys, these two here, we would call those cations. This thing here, we'd call an anion, and these would just be the neutral atom. Okay. So we've got our charges. Those, again, for the main group elements, those charges don't really change. So calcium, you're never really going to see it forming a 3+ or a 1+. It's going to specifically form a 2+, okay? These transition metals in the middle, they do weird things depending on the situation. Sometimes they form +2, sometimes they form +4. And so you can't read their charge or get their charge off of their position on the periodic chart. Next thing we're going to move into, because we've talked about, protons are not something we can mess around with, right? If it's that element, it needs to have that number of protons. Electrons can change. If we change the number of electrons, it changes the material's charge. It doesn't change what it fundamentally is. Aluminum versus aluminum 3+, they're both still aluminum, but the aluminum 3+ has a slightly different charge. We can also play around with the number of neutrons, okay, or the number of neutrons can vary. So the term isotope, ISOTOPES, you may have heard something called a radioactive isotope, right? Radioactive decay. Isotopes in general, outside just even being radioactive, but an isotope is an atom that has the same number of protons, so it's the same element, but it has a different number of neutrons. So we're messing around with the number of neutrons. What are the properties of a neutron? A neutron has mass, right? So yes, so has mass, but no charge. So if I mess around with the number of neutrons, let's say I add or subtract neutrons, It's not going to change the charge. That's something electrons do, but it will change the mass. It'll make the material heavier or lighter. It doesn't change the material because it's not changing the number of protons, but again, it does change its mass. So all elements have their own unique percent of what we call natural abundance of isotopes. Certain isotopes just naturally form more than other isotopes. So let's look at neon. And there are two types of isotopes. There's radioactive isotopes and stable isotopes. Radioactive isotopes are isotopes that have a certain number of neutrons that are just unstable and they want to decay or break apart. Stable isotopes are happy and they don't want to break apart. So let's look at neon. If we see a neon light and it has neon gas inside a tube that's then being excited with some sort of electrical current. If we were to open this up and look at the neon, not all the neons would be the same. There would be different isotopes of neon. There would be this thing called neon 20, which is a majority of what we have, about 90%. We'd have neon 22, which is just under 10%. And then we'd have a small sliver of this thing called neon 21. Now, do you notice how these are written as neon and then it has a dash and the 20 is in full text? It's not superscripted. That is meaning or indicating that that's talking about the atomic mass, not the charge. Okay, so charge happens in the upper right-hand corner, like up here. If you see it formatted like this is talking about the atomic mass. And what does atomic mass equal? Atomic mass equals protons plus the number of neutrons. Do we include electrons in atomic mass? No, because electrons are so tiny. Doesn't mean they're not important. They mess around with charge, but they don't have anything to do with mass. So when we talk about neon 20, well, first of all, let's talk about neon. What makes neon neon? Look on your periodic chart. If it's neon, it has to have 10 protons. Okay, that there's like no debating that. So neon will always have 10 protons. Doesn't matter if it's neon 20, neon 21, or neon 22. There are 10 protons in each of those case scenarios. What does change is the number of neutrons. So in neon 20, this number here, which is the atomic mass, is protons plus neutrons. So I know what my protons are. They're always 10. So my neutrons is whatever's left over. So we take the 20, we'll subtract 10, and we have 10 neutrons left. So in this case, we have an equal number of protons and neutrons. Sometimes students will think, oh, well, isn't it always the same number of protons and neutrons? No, definitely not. Okay, neutrons can be, usually they tend to be more than the number of protons you have. If we have neon 21 here, we've now gone into a heavier version of our neon. We haven't changed the charge. We haven't changed what it is, so we haven't changed the protons, but we've made it heavier. The only way to do that is to add another neutron. So in this one, we have 11 neutrons. This is 10 neutrons, this is 11 neutrons. Neon 22 will have 12 neutrons to it, heavier by 2. all the elements have these different isotopes. I don't expect you to have the isotopes memorized, but I do expect you to be able to like use isotopes and understand them. So let's look at some other ways that you can write an isotope. One way is to write the symbol here, and then to put the mass number in the upper left-hand corner and the atomic number in the lower left-hand corner. So neon 20 with the 10 in the bottom. I will write it like that sometimes, or sometimes I write it like this, neon 20, and I won't write the 10, because if it's neon, isn't this always going to be 10, right? This is sort of, these two things are always glued together. It's like redundant information. So you may see it like this, or you may see it like this, or you could see it like this, neon dash big 20, or sometimes they write it as neon, the full name, dash big 20. Okay, so there's a couple different ways of seeing the isotope. All of these numbers, again, are referring to the atomic mass, which is protons plus neutrons. So, okay, got that. I'm going to write a couple isotopes out for you, and I want you to tell me how many protons and how many neutrons are there. Let's do chlorine 35 and chlorine 37. Okay, I want you to tell me the protons and the neutrons for each of these. I'll give you like a minute, it shouldn't take too long. All right, so if we are dealing with chlorine, chlorine on the periodic chart is number 17, so the protons should always be 17. That's not up for negotiation. So I'm just going to put 17 for both of them. The number of neutrons is dependent on what the mass is. So if I have a mass of 35, well, 35 minus the 17 is going to leave behind what? 18 18 neutrons. So for this first one, we've got 18. For the second one, we're going to take 37 because we're two bigger, subtract 17, take out the protons, and we're left with 20. So we have 20 neutrons. So this one, chlorine 37, is heavier than chlorine 35. Chlorine 37, my master's thesis was in stable isotopes of specifically perchlorate contamination, which is ClO4 minus. So I looked a lot at the isotopes of chlorine 35 and chlorine 37. And what you find is with chlorine 37, it's a heavier element, so it tends to drop out faster in certain circumstances. There's also oxygen here. So we have oxygen 16 and oxygen 18, oxygen 18 being the heavier one. Again, these things will behave in certain ways. So like, let's say you have water, H2O. There's oxygen in there that has both of these guys. Well, if it's sealed up, let's say in a rain cloud, the first thing that's going to rain out is going to be the heavier stuff, oxygen 18. So close to a shoreline, because storms tend to form over the ocean, closer to a shoreline, the water that you find on the ground is going to have a higher quantity of oxygen 18 to it. As you move inland, your water will become heavier with oxygen 16. So I know that in the past, it's been decriminalized at this point, but they've used stable isotopes to figure out like where marijuana is grown or poppy seeds are grown, because they can figure out, oh, this is really heavy in oxygen 18. These marijuana plants were probably grown close to a shoreline. They can also use ratios of stable isotopes to figure out where you have traveled. So They've done a lot of like counter-terrorist stuff where they've taken people's hair samples and they're able to see where they've traveled by isotopes that are trapped in their hair. You can also fingerprint contaminants. That's what I did. I looked at these isotopes and I fingerprinted to see if the Department of Defense was polluting perchlorate in the Great Lakes. They were not. It was runoff from fertilizer. You will find that things that make really good fertilizers also tend to make really good explosives. Kind of go hand in hand. Okay, so got this idea of isotopes. Actually, I want to give you something else with for practice. Let's where did you go, whiteboard? Okay, let's say we have okay. I want you to tell me the number of protons, neutrons, and electrons for this thing right here. That is supposed to be an A. A, L, 3 plus, 26, and 13. Okay, so you've got combination of information about charge, mass, and identity. So you give me protons, neutrons, and electrons. You better at least be able to give me the protons. I'll give you a minute for that. Okay, so protons, if it's aluminum, it's 13. You can get it from here. Also, you just know that it's aluminum. So look it on your periodic chart, it's 13. The number of neutrons is going to be dependent on what the mass is. So I have a value of 26 for my total mass. So let's subtract out 13 because that's the protons. And whatever's left will be my neutrons, which happens to be 13. Okay. The number of electrons, that has to do with the charge. So we do have a charge on this particle. Charge 3 plus is going to equal my protons, which is 13, minus my electron value. All right, well, I need to subtract 10 out in order to get the positive 3. So we'll go with 10 here. So 13, 13, and 10. Grayson, you were right. Fine. So make sure you know how to manipulate, play around with those sorts of things. Here, I want you to write an element, like the symbol and what it would look like for something that has 26 protons, 28 neutrons, and 23 electrons. I want you to write something that looks like this, kind of going in the reverse direction. Okay, so writing, I would say first off, write the symbol. So what has 26 protons? I mean, the only option is iron, right? It's number 26. I could put a 26 down here too. And then I need to put the atomic mass up here. So the mass is going to be the protons plus the neutrons. So 26 plus the 28 will give us 54. This is iron 54. And then do I need to add a charge? I do, because these numbers are different from each other. So in order to get the charge, I take my protons and subtract my electrons. 26 minus 23 would give me a positive 3 or 3 plus. And so you want to be able to go in either direction with that. When you look at the periodic chart, and you think about atomic mass, and let's go here. We're looking at these atomic mass numbers, they're decimaled, which is kind of weird because it's like, well, isn't the atomic mass the protons plus the neutrons? Shouldn't that be whole numbers? Why would we have like a half of something? The reason that these numbers are decimaled is because they are the average of all of the isotopes with their relative abundances. So for instance, when I look at carbon, which is number 6 here, its atomic mass is 12.01. Most of the carbon out there is carbon 12, but there is a small percentage of carbon 14, which makes up this additional 0.01 that's giving us that value. It's kind of like when you average your grades in a class, your tests are worth more than your homework, so you have to give them more weight, whatever that percentage weight is. Same thing here, like neon is mostly neon 20. There's a little bit of 22 and a little 21, but it's mostly neon 20. So when we average these out with their relative masses, the overall mass should sit close to neon 20, but it's going to be slightly higher than neon 20 because we have a small percentage of these heavier elements. So if you look at your periodic chart, what is the mass of neon? It's 20.180. That extra little bit is because there are some neon out there that exists in a heavier form. So how do we calculate that? Well, this is the formula, the generic formula. So the total atomic mass, or the averaged atomic mass, is going to equal the fraction of the isotope, which is just the undoing the percentage. So if it's 66%, you would do 66 divided by 100, or move the decimal over 2 to get rid of the decimal. So you take the fraction of the isotope times the mass of the isotope, and you add it to the fraction of isotope 2 plus the mass of the isotope 2 plus fraction of isotope 3, mass of isotope 3. How many times do you do this? For however many isotopes you have. So if you have 2 isotopes, you average 2 things. If you have 6 isotopes, you have to do 6 of these. Sometimes people will go, well, when you average, can't you just add them all up and then divide them by however many you have? That would be the case if they all had an equal weight, but they don't, right? They have different percentages. So we need to take that into account. So let's look at chlorine. Chlorine has chlorine 35, and sometimes in these problems, they will give you a mass with a more specific decimal value. Use that. Okay, so it's chlorine 35, but it's really 34.97, so use that. So chlorine 35 makes up roughly 75.77% of the chlorine out there. So most of the chlorine out there is chlorine 35. But the remaining quarter, 24.23%, is chlorine 37, okay, or is really chlorine 36.97. So, 3/4 of it is chlorine 35 and 1/4 of it is chlorine 37. So I know when I average these out, my number should end up closer to chlorine 35 than 7, but it's going to be greater than 35. One way you can check and make sure you've done these correctly is your end number better fall between 35 and 37. If it falls outside of that window, you've not averaged it correctly. That'd be like getting a D and a B and your final grade is an A. No, it doesn't work that way. Your grade is going to fall between the D and the B. Okay. So we take our percentage, 75. You only see the whiteboard. Is that the case for other people? Am I just talking to a blank screen? Let me close up the whiteboard. Okay. So here we go. So we take the chlorine, we take the percentage. Sorry, I'm totally spaced out there. Take the percentage and divide it by 100. Or we take the decimal and we move it over 2 places. That's what this number is. Okay, you see this? This is the decimal percentage. We take that value and we multiply it by our mass. So if it gives me the decimal mass, I'm going to use the more specified mass. And then we're going to add it to however many isotopes we have. So here I've got 24.23. I'm going to move that decimal over 2. That goes right there. And then the mass of it goes here. When we multiply these out and then add them together, we get a value of 35.45 AMUs, which is the number that's on the periodic chart. Some people say, oh, well, why would I do all these calculations if I can just look at the number on the periodic chart and get the right answer? Well, you might get a like fictional element with fictional masses. So don't assume that you can just look at the mass on the periodic chart. So let's work on one of these. Well, you guys will work on one of these. Gallium has 2 naturally occurring isotopes. Okay, there's gallium-69, which actually has a mass of 68.9256. And its abundance is 60.11%. So the majority of the gallium out there is gallium-69. And then there's a minority, or 39.89, which is gallium-71. Its actual mass is 70.9247. Calculate the atomic mass for gallium. So I'll give you guys 3 minutes for this. You have only 2 isotopes you have to play around with. Oh, I'll be back 2 minutes. Okay. So when doing these problems, make sure that you get the percentage, you get rid of it. So you divide it by 100% per 100 cent, 100 cents in a dollar, right? So we want to move that decimal over two places. So it becomes 0.6011 and 0.709247. If you do these problems and your number is like way bigger than the two masses that you have, you probably didn't move the decimal over two. So do that. So we get our fractional weight for each of these. And then we take that value and we multiply it by the corresponding mass. Also, don't flip-flop the masses with the wrong percentages. In this case, we end up with a final value of 69.72 AMU. Round to 2 sig figs here, or rather round to 2 decimal places, 4 sig figs, because this had only 4 significant figures. Does this number fall between the two original values? Yeah, it was what, 68, 9 and 71, and we're at 69.7. Yeah, so it falls between, so it makes sense. Yeah, so let's do, I wanted you guys to do one more of those. I'm not gonna find it in my email. Okay. So just to test you, let's do the one with titanium. Titanium has 5 isotopes. Okay, so you get to do 5 of these. This doesn't give a more detailed version of the mass. So for titanium 46, you can just use 46 as your mass, right? You don't have to use any sort of decimal number. So we've got titanium 46, 47, 48, 49. I don't know why these aren't superscripted, 49 and 50. The majority of it is titanium 48. So I'm assuming my number will probably hang out around titanium or around a value of 48. But I want you to go ahead and calculate all of those. So I'll give you another 3 minutes for that one. All right, so there are 5 individual isotopes that we have to take into account. The first one has a mass of 46, and we're going to multiply it by its percentage, which is 0, or rather 0.080. Okay, the next one is a mass of 47, and we're going to multiply that by its percentage, which is 0.078. Remember, we want to move the decimal over 2 hops, so you'll fill a 0 in there. The biggest percentage here, 48 times 0.734. We've got 49 times 0.055, and we've got 50 times 0.053. All right, you calculate all those and we add them all together. And we get a total value of 47.92. I got 47.92. 47.92 AMU. Technically, since these are such kind of cruddy numbers, we would round to 2 sig figs, so it would be 48 AMU. So yeah, I'd be fine if you gave me the 2 decimals though. And so what is this saying? It's saying our mass is slightly less than 48, which makes sense, right? Our majority of it is 48, and the 2 lighter ones are in a slightly bigger percentage than the 2 heavier ones, right? These are in the 7 and 8%. This is in the 5%. So we're kind of leaning a little bit more towards the lighter side, which is represented in the number here. Questions on that, on how to calculate your average atomic mass? Again, you could always be like, well, I'll just look titanium up on the periodic chart. There it is, okay? But that's not always going to be the case, because if you have some made up element, nevidium, and it has some made up values and percentages, you're not going to see it paired up on the periodic chart. All right, so that is it for chapter 4. You guys are good to go. You're covered through everything for test 1. Next week, we'll start up information for test 2 stuff. We'll start on chapter 5. Again, the test is not taken during any like official class time. It's taken somewhere between Sunday morning and Monday evening. So you take it at your convenience between those time periods. I am here to hang out. So if you have any questions or anything you want to go over, or any example problems you want to work on, just feel free to ask. If you're good and you're done, then I will see you next Wednesday. I'll send you guys an email sometime over the weekend to remind you to take the test. Okay, don't miss the test. There's not a whole lot y'all have to do in these online sections, except turn in some assignments and take the test. Okay. Awesome. So if you're going, bye. If you're staying, give me a question and we can work on something. And I post the YouTube video as well, so we can go back and study. Yes, I can post the YouTube videos. Lauren, if you don't see it tomorrow, send me an email tomorrow. My computer, it takes my computer like 2 or 3 hours to process the video to convert it. So that's why I don't do it right after the lecture. So Lauren, if you don't see it tomorrow, just send me a message, okay? All right. Other questions, you can throw it in the chat, or you can turn your mute off. Have any questions about stuff?
On the test, will there be like problems with the specific heat and the joules per gram degrees Celsius?
Mm-hmm.
Is there any way you could tell me how many questions will be on the test?
I don't remember. I think there's like somewhere between like 20 and 30. They're multiple choice.
Okay.
Okay. But multiple choice sometimes can be a little tricky because it can like lead you in the wrong direction as well, right? Because it can give, it tends to give the answers that are most commonly, people most commonly mess it up with. So, yeah, so don't have a false sense of security with it being multiple choice. That's all I'm saying.
There's not a test like review that we can look at before? Or anything?
No, there are objectives. So let me share my screen.